Okay, welcome to the last panel of the day. Really excellent conference, I think, here in Brooklyn. You may have seen me this morning, but for those of you who haven't seen me, my name's Venetia Lannon, and I am Vice President at Con Edison for Environment, Health, and Safety, but I am also a NY-GEO board member. Really excited to be here moderating this panel on energy, thermal energy as a service. So this is the last in the incentives and financing track. I am just going to say a word of introduction and introduce our panelists. We've got a really great lineup for you who's going to, I think, take you deeper into this subject, which I'm super interested in. But thought I might just start by just defining energy as a service. I'm sure many of you know what it is, but it doesn't hurt to kind of just reset on the definition of energy as a service. And this is... energy as a service is a business model where customers pay a recurring subscription fee rather than making an upfront capital investment into energy assets. Does that make sense? Like sort of a subscription for energy. Under this model, a service provider assumes responsibility generally for the installation, operation, maintenance, and financing of the energy system on behalf of the customer, and then the customer pays for the energy service on a subscription or pay-per-use basis rather than owning the energy infrastructure. Just so I thought I'd sort of set the groundwork there for sort of what is energy as a service. We're going to be hearing more from our three panelists, and I'm going to introduce them right now. So first up, we're going to hear from Cameron Best, Senior Director of Business Development at Brightcore. Then we're going to hear from Tim Banach. I got that right, Tim? Yes, Tim Banach, Vice President of Development at Endurant. And then batting cleanup, last but certainly not least, is going to be Michael Albertson, President of SHARC Energy. We're happy to have Michael here with us today. And what you're going to hear... Cameron and Tim are really going to set the stage and sort of help further define energy as a service and focus on some of the challenges of this model. Spoiler alert, all is not rosy in the energy as service world when it comes to district geo. But they are also going to, Tim in particular is going to tee up some characteristics of what sets us up for success in this space, namely energy as a service in district geo. And then Michael is going to take us to an adjacent but very much related space, namely wastewater heat recovery, that complements all geo projects. But he's going to share with us some novel approaches that they've found in that world that SHARC is taking to look at energy as a service, some fee models that have been successful. So with that, I'm going to turn it over to Cameron, and welcome to the stage, Cameron.
Right. Thank you to all the conference warriors who are here at the last panel on the last day of the conference. So as Venetia mentioned, better? Okay. So as Venetia mentioned, I'm with Brightcore Energy. We are an electrification solutions provider. So we play in the electrification space. Our core technologies are geothermal heating and cooling, LED lighting, as well as solar PV. And I think it's good to look at these three projects, or these three technology verticals on the screen, because we have done as a company quite a bit of energy as a service within the LED lighting space. We've also done quite a bit of energy as a service kind of through the PPA model in the solar PV space. So all that is to say that we know the energy as a service and that structure well. But what I'm going to do today is talk through some of the challenges that geothermal as a technology has. Specifically, if you've been sitting in this room, you've been hearing about some of those challenges from Ryan, from Keith, and others on the IRA sessions. And I will go through a couple of those here today. And then we'll talk about how the space has changed, right? A couple years ago, energy as a service was really being driven to finance projects, but the IRA has stepped in a pretty significant way and maybe alleviated some of that previous interest and demand in energy as a service. So with that, I wanted to start with a macro view. What are we really trying to accomplish when we talk about energy as a service? And this is very broad, but broadly the goal of energy as a service is to reduce the capital costs of geothermal projects such that counterparties without access can access geothermal technology, right? So we're trying to reduce the barriers to geothermal technology through a financial product. Because of some of the challenges associated with how the IRS treats this technology, we're having very limited success in achieving that objective through the energy as a service model. So the biggest challenge that we have, and Keith spoke about this earlier today in this room in the IRA panel, we cannot have multiple legal tax owners of a geothermal system. So we can't have somebody own the ground loop and somebody own the heat pumps and somebody own the distribution throughout the building. If we have two separate owners, no one gets the investment tax credit. And as we all know, that's a really important driver to making these projects pencil and making for an attractive energy as a service project. So that's kind of hurdle number one, and that's really set by the IRS. The other challenge that we often encounter is when we have, when we have counterparties who may not have good credit or strong credit, and they can't access credit channels themselves, that often poses a pretty significant counterparty credit risk to energy as a service providers. So, while energy as a service providers, they're, willing to take some credit risk, oftentimes those who do not have good credit aren't in a position, to be an energy as a service off-taker because the energy as a service provider is not willing to take on that credit risk. So that's another challenge that we have seen. Again, back to an IRS challenge, because the geothermal is a non-removable asset. If I am paying an energy as a service fee, and all of a sudden I become non-performing on that payment, the geothermal developer cannot come and pull that system out of the ground. So they can't take that system and sell it elsewhere. So again, that's another structural challenge. And essentially the impact of that is that it can't be really deemed as an off-balance sheet asset. And that's what where a lot of the interest in energy as a service comes from, is being treated as off-balance sheet. So again, we have a structural challenge in achieving that. Then lastly, bonding covenants. Since we can't treat this as off-balance sheet, if you are taking money from a DASNY, for example, they'll often place restrictions that limit your ability to take part in an energy as a service type structure with the geothermal technology. So I would say from a structural perspective, we have some serious headwinds for energy as a service until, and I don't know if Ryan's in the room, but until, hopefully Ryan is continuing to work on this, and there's plenty of folks in this room who know of this issue and are working on it. But until some of these structural challenges are resolved, I'm going to kind of propose an alternative solution to help us ultimately achieve and expand geothermal technologies. All right, I apologize. A couple of the graphs did not come through here. But one of the things I think that has obviously changed in the last 2 years is we've entered a new paradigm under the Inflation Reduction Act, where these projects are receiving really significant incentive funds at the federal level, and also there's some incredible incentive programs at the state and local level as well. So historically, we would be looking at energy as a service to kind of solve long paybacks. We were looking at 10-year paybacks, 12-year paybacks. But with the ability to receive Inflation Reduction Act investment tax credits, as well as state and local incentives, that's just not the case anymore. Oftentimes, if you're already going down the path of electrification, you're looking at an electric boiler or an air source heat pump. Generally, what we're seeing on both new construction, multifamily projects here, we have a 270,000 square foot multifamily building. New construction, they have a year one payback compared to an air source heat pump alternative. Another example here, we had a 145,000 three-building system on a higher ed campus, a 1.3-year payback. So these long paybacks are just not as much of an issue now with the investment tax credit and the local and state entities stepping in with some incentive funds. But this does create a new challenge. And the new challenge, I think, that could use some focus from commercial lenders, from green banks, from anyone who's providing finance in this space is gap financing. So what this sets up when we're claiming investment tax credits is we will commission a system, and then there will generally be a year and a half before that entity receives the investment tax credit. I think that's an area where we could use more financial products, and ultimately we would enable more projects to happen if we had, potentially low interest loans to step in and close that gap, whether it's from green banks or state incentive programs. I think that's an area where we could really drive much more project growth with a simpler structure than energy as a service. So I know that's not a very rosy picture. I feel like this was my Frank Costanza airing of grievances about energy as a service. But it's a great solution for technologies where it doesn't have structural challenges. I would say if we can alleviate those structural challenges, this is a very ripe market for energy as a service. But until then, we could use some more help from commercial financiers and partners to solve the bridge financing gap that the ITC sets up. So thank you.
Thanks, Cameron. Good afternoon, everyone. Thank you for sticking around. Michael told me that for everyone who stays till the end, he's going to buy him a beer. So thank you, Michael. Maybe I'll be buying the beers. Okay. Thanks. Okay. So Tim Banach, Vice President of Development with Endurant Energy. We're a project developer, an EPC provider. Worked on various technologies on my time at Endurant, fuel cells, cogeneration, and geothermal as well. And so I'm going to talk to you a little bit about my experience with energy as a service. And I've worked on developing and trying to support the commercial development of thermal energy networks, specifically for large multi-building districts in various areas of the country. These have included, major sort of master plan redevelopments, pretty large scale, different building types, residential, commercial, retail, open space, data centers, and ultimately I've looked at various models for trying to commercialize energy as a service, particularly for GEO, although we offered energy as a service for those other technologies as well. And there was a lot of design diversity in these projects. So, looked at ambient temperature loops, central plants with 4-pipe distribution, bore fields, energy foundations, sewer heat exchange, Michael's going to talk about, using kind of local water bodies for thermal exchange as well. And so in the Bay Area, there was 3 different master developments there, different developers, pretty large. These were between 700 and 1,000 acres each, so pretty large developments. These are decades-long redevelopments. In Chicago, there's about a 50-acre redevelopment that we worked on there. Project in Canada, I'll talk a little bit about later. And then in New York, through a lot of help from our friends at NYSERDA, looked at, I think, about 10 different developments, different district thermal energy networks, and did pretty in-depth studies around each of those. So that is to say, I've dealt with a diversity of kind of size, customer type, building type, geothermal technology type, system design, and have looked at energy as a service for each of these. Okay, so the value propositions, I'm not going to run through in too much detail because you've heard a lot about those today and yesterday. But these are the kind of similar themes we've heard that geothermal systems can offer. And it's essentially cleaner, quieter, fossil-free operations. And the larger districts, the more you can aggregate thermal loads, the more efficiencies you can get. And so, the benefits to off-takers and the building owners is really, it's on the technical side, and it's on the operational side in terms of OpEx. Okay, so what are the challenges for energy as a service? And, I tried to boil these down into really what I've seen the challenges are. I could go into great painstaking detail about the challenges for each of those projects, but ultimately it's this idea of this long-term commitment from both parties that's been somewhat of a challenge, and there's a certain amount of risk involved. I call it occupancy risk or revenue risk for the asset owner, because ultimately what's happening here is the real estate developer is betting on the geothermal energy as a service provider that they're going to build and operate a system for 20, 30 years and deliver on those performance guarantees that are part of the energy as a service contract. If the geothermal provider can't do that, the building owner has a building that, with an HVAC system that maybe doesn't work as well or at all, and that's a problem for the developer, for the real estate owner. And alternatively, the thermal energy network or geothermal developer is banking on the fact that the real estate developer is going to construct a building on time and get them occupied, because that's where the revenues come from. And so there's a fair amount of risk for both parties, because this ends up being a long-term commitment. As Cameron mentioned, you can't repurpose the geothermal system once it's been installed. And so there's some risk there. The other challenge I've seen is, energy as a service, particularly for geothermal, is viewed as some alternative to a business as usual approach, right? Business as usual being whether your system's electric or gas-fired, hooking up to the local distribution utility. And as an engineer once told me, it's kind of stuck in my mind, he said, no one ever got fired by connecting to the utility, making that decision. And he's right? That's the business as usual approach, and no one gets fired for doing that. So what have I seen that I think are ingredients for success? And again, I'm sort of summarizing here in the interest of time, but keeping it simple is obviously a good strategy here. So these super large scale developments are phased, and so it's often wise to focus, if you're constructing a new thermal energy network, to focus on phase one, trying to find a large anchor tenant with a phase one district thermal system where the finance works given that anchor tenant, right? So if you can find sort of that one anchor tenant, that one large building that can serve as your phase one off-taker, and it makes the project pencil, then you have a good place to start. Because once a project is operational and stabilized, building out upon that is much easier. Having a single contractual counterparty is also simplifies everything. It's a project in Canada, and I think it was about 10 or 12 buildings, but they had a different developer for each building. And so rather than negotiating a single offtake contract, we now had to negotiate with 10 different offtakers and try to come to similar terms, which is quite difficult to do. And then, finally, thinking about incentives and potentially introducing new incentives that really support long-term interconnection. You say incentives and people think IRA and nice sort of grants and clean heat, and all those are important and essential, and they help buy down the CapEx. But I'm talking a little bit more about incentives that will keep customers connected for the long term. So one example might be, some new construction projects where this type of system is the base case, is built into the building, right? We've worked on a couple of projects where it's a new, townhome community, and each townhome is built with a water source heat pump connected to a common thermal energy ambient loop or bore field. And, once you build it and construct it that way, it's very unlikely that your buyers are going to exit that agreement, right? Because there's a certain amount of inertia there built into what they've purchased. And there's a lot of examples of successful projects that have done this throughout the country. The second would be, the third would be, potentially thinking about carrots and sticks that municipalities could introduce that could help nudge these thermal energy networks towards stabilization. And there's certain jurisdictions in the country that are offering, for example, property tax relief or property tax credits for buildings that undertake certain energy efficiency improvements. And those property tax credits are, 3 to 5 year abatements or reductions in property tax if a certain energy efficiency measure is undertaken. And so by doing this, you're incentivizing building owners and building developers kind of for the first 5 years. And if it was applied to a district geothermal system, you would get to a point where that project is now achieving stable operations. I haven't seen it specifically for geothermal, but I think that could be a potential something to think about. And my last point I'll make is to look to our neighbors of the north. Vancouver is a pretty good example of where this has been successful. Over the last, say, 15 years, which is a relatively short period of time, Vancouver has adopted a number of neighborhood thermal energy networks, and they're diverse. Some are utility-owned, some are privately owned, some are geothermal-based, some are not, some are biomass-based. So there's a real diversity of system types there. But one aspect I think that helps support that uptake is, in addition to incentives, in some of those neighborhoods, there's a mandate for new construction to connect to these thermal energy networks. And so rather than just having a bunch of carrots, you have a stick that says you shall connect to this network. It's going to be efficient, it's going to save you on operating costs and deliver all these benefits, but you kind of take the choice away from the building developers and owners. And you are able to ensure that you have long-term connection by users and stabilization of the overall system. So I'm going to wrap it up here because I'm getting flagged. But I think that, when I think about incentives, I'm thinking more in terms of sort of longer term, maybe municipally led incentives that can help, establish these systems so that once they become stable and achieve successful operations, they kind of continue on. I think overcoming that initial interconnection and stabilization has been the challenge. So, thank you.
Okay, Michael Albertson here. Move this mic down. I'm the shortest one on the podium today, so everybody hear me in the back? Okay, so this is going to be really fast-paced because we're somewhat limited on time, and Mr. John Shavacco asked me to cover a little extra material, so I'm going to be moving at a pretty fast pace. Just to kind of lay the slide deck out, I'm going to set the stage with what's the value of wastewater, and then also briefly cover a couple different technologies to harvest thermal energy from wastewater, what we do with it, 2 different ways, and then I'm going to hit some case studies that I was asked specifically to refer to. So here we go. So to put the value of wastewater in perspective, US DOE has put a number out saying that there's 350 million megawatts of thermal energy that's basically discarded down the drains every day. And since we're in New York City, one of the things I just want to take a look at here, just bring it in perspective, is in a New York City DEP, they process 1.3 billion gallons of sewage every day. 1 million gallons of effluent equals 1 megawatt of thermal energy, okay? So put that in perspective, there's 1,300 megawatts per day that is being discarded down the drain with wasted thermal energy just in the New York City area alone, okay? So what do we do with that? It's gonna require some specific technology in order to take care of it. Specific technology, two different ways of doing it. On the left-hand side, there's a product called a piranha unit. It is a water-to-water heat pump. It is an effluent heat pump. It's a wastewater heat pump, so it has a refrigeration cycle in there. Most everybody in the room is familiar with water-to-water heat pumps. The difference is that we have a heat exchanger in this piranha unit that is a tank-style heat exchanger that can accept solids, it can accept particulates in there, and it doesn't clog up like typical heat exchangers. So the piranha unit is typically used in multifamily housing, student housing, senior housing, hospitality, hospitals, commercial laundries. That's kind of the small medium, and you put multiple of these on a job. You go into the larger size projects, medium size and larger size, you get into industrial and commercial, which again would be hospitality, breweries, hospitals, commercial laundry, textiles, pulp paper, district energy systems. And the SHARC unit does not have a refrigeration cycle in it, okay? It is just a very large capacity, large scale, large volume thermal energy harvesting plant that transfers that thermal energy to a condenser loop, an ATL, or a building. So again, piranha unit, I'm not gonna hit every point on these slides just due to time, but I wanted to include those in the deck because you guys are gonna have a copy of this deck and you'll be able to look at it. But the piranha unit, you know, the supply, we talked about the source on the piranha unit. You got the source and you got the load. So the load side, or the deliverable on a piranha unit, is basically 140-degree potable water, and depending on the source temp, that can be 3.5 COP or 350% efficient, more efficient than an electric boiler. So 3.5 COP up to 5.5 to 6 COP, depending on the temperature of the source coming in. So it is a double wall vented heat exchanger, so it's all NSF rated for potable use. So deliverable in the piranha unit, take any kind of effluent, any kind of wastewater, and deliver 140 degrees. So that's a line diagram. I don't know what happened to some of the graphics on here. I apologize for that. But that thing up there, it says it's a compressor. So it just shows a line diagram of taking the wastewater in. You got the cylindrical tank on the right. You go through the refrigeration system. We deliver 140 degrees out the other side. Now, some of the cool things we've done with the piranha unit is we can add an extra heat exchanger. So the reason we add this extra heat exchanger is you can also use this unit to extract heat from a building or multiple buildings. And if you extract heat from a building, you're basically providing cooling, right? So you can do that, or you can use that to temper, and this crowd is going to resonate with you. You can use that to temper or retro commission a ground heat exchanger that may have been installed years ago. They changed the load so the temperature's creeping up or it's creeping down. We can condition that loop. If you're in an urban environment like we are in New York City, the job is going to design out and say, okay, I need 300 boreholes 500 feet deep. Well, the space doesn't allow you to drill 300 boreholes, but it'll allow you to drill 150. So you can intentionally short loop that ground heat exchanger, and we can take up the slack on that ground heat exchanger and control the temperature of that ground heat exchanger and control that creep so that the ground heat exchanger can still deliver 55 to 80 degree entering fluid temperature to the hydronic systems in the building, okay? So here's an example of tying the extra heat exchanger into a ground heat exchanger. So it can reduce the cost, CapEx. We're talking about, energy service and ESCOs. CapEx is important. So if you're in a bind with the ground loop, you need to get it back in check. You can't put enough ground loop in instead of using a traditional hybrid system. Then you put a piranha system in. All that wasted energy, or that energy we're capturing from the ground heat exchanger to get back into play, can then go into heating domestic hot water, snow melt, de-icing, whatever it is. So that's a piranha unit. The SHARC unit. The SHARC unit is totally different. Piranha unit's a water-to-water heat pump. The SHARC unit is a large-scale, large-volume heat harvesting, heat transfer device. And so there's 2 sizes currently, and a third coming out, but the smallest one with running the whole SHARC plant, the motors, the pumps, it costs us kW to run that SHARC plant. We're delivering megawatts. So our smallest unit delivers 3/4 of a megawatt, and our 880 delivers 1.6 megawatts. So the next one out will be a 3.3 megawatt, okay? And again, read those whenever you get the slides. This is how the whole thing works. You've got wastewater inlet. You can see it on the left. It's coming in, goes through a macerator. Macerator's life is making small chunks out of big chunks. So the solids go out the bottom, back to the wastewater outlet. It then goes through the SHARC unit, which is the barrel you see there. It's got a blue motor on top, drives an auger, pushes the solids down. 3 mil or 1/8 inch material comes out with the majority of the flow, and it goes into a wide gap heat exchanger. Our particulates are 3 mil that we introduce into this wide gap heat exchanger. Wide gap heat exchanger can accept 9 mil material. We keep the velocities up so you don't have any settlement in that heat exchanger, okay? Very simple. Here's a line diagram. On the bottom left, you can see a wastewater holding tank. This wastewater holding tank on either the piranha or the SHARC system can be filled with effluent from a building, multiple buildings, or city sanitary lines, okay? So again, out of the wastewater, through the macerator, through the SHARC, the solids out of the SHARC on the bottom, you go to a heat exchanger, and in this example, this is energy recovery from the wastewater. We use that to heat the condenser loop up so the building operates more efficiently with your hydronic system. This example, since it's a passive thermal energy transfer system, it's kind of like how do it know, right? So this is a energy rejection or cooling. So if you need to cool a building or a series of buildings or an ATL, you can actually take that temperature, run it through the same process. You can take that fluid, run it through the same process through the heat exchanger, and we're actually moving that thermal energy you don't want in the building or ATL, providing air conditioning, cooling, back into the sanitary lines, okay? This is an example with a SHARC system on a single building with a condenser loop. It's driving water source heat pumps, water-to-water heat pumps, fan coils, water-cooled refrigeration devices. If you have a condenser loop in multiple buildings, and this really gets into an ambient loop or an ambient temperature loop, I'll call it an ATL, then we condition this ATL or this ambient loop. As I mentioned earlier, if you have a ground heat exchanger that's overheating or you couldn't put enough ground heat exchanger in, you need to go back and retro commission it, then you simply tie that into the ambient loop. So we can then keep the temperature swing in that sweet spot range to maximize the performance and capacity of the water source heat pumps, geothermal heat pumps, water-cooled reefer stuff, okay? One quick example. Here's one of the 3 projects that Mr. Shavako asked me to just touch on real quick. This is what we call the Alexandria project. It's in Seattle. And King County basically is the county around Seattle. It basically goes from SeaTac Airport, halfway in between Seattle and Tacoma. So King County and McKinstry and Alexandria Life Sciences, they partnered up with us. And so this is a project. It's 6 buildings total, 1.6 million square feet. And you can see in the picture on the bottom, this is we call it a baby SHARC. So this is 660, this is a SHARC 660, so we'd be putting out about 3/4 megawatts of thermal energy that we recovered or harvested from King County sewage. This is a public-private process, so it's a little bit different than a normal energy as a service or ESCO or something like that, but it's public-private. The cool thing about this is that King County has recognized the value of wastewater energy transfer in the sewage that they have throughout King County, which is hundreds and hundreds of miles. So they have set up a program where they're giving private and public buildings the access or an easement, a tap easement to their sewage lines, okay? They went a step further in that they have documentation on how they set their program up. You can get hold of me or get hold of Aaron Miller over here to my left in the front, and we can provide that information to you, but it's how they set this whole up, the whole system up, so they can track how many BTUs in temperature with volume on block by block are being taken out of the sewage lines, or how much energy is being put in. That way, if somebody files to say, hey, I want a wet system on my campus or my series of buildings, then they can make a judgment of, okay, we're either overloaded, we're underloaded, sure, knock yourself out, or no, you can't do it, okay? So the outcome on this is, with just wastewater energy transfer being utilized on this campus, and it's a health science research campus, just the wastewater energy transfer was able to take care of 99% of their target for carbon emissions reduction, okay? So that's pretty cool. The other thing is 70% of the heat that is needed in this research facility comes from wastewater energy transfer, all right? So here's a little different system. So this system, we'll just call it Leland Living. It's a campus. It's actually developed and owned by the Musqueam tribe, which is part of the First Nations in British Columbia. And it's a 22-acre mixed-use facility. There's 1.3 million square feet of indoor space. There's residences, there's apartments, there's multi-use, there's a grocery store, community center, and you can see the campus, photo of the campus on the top left. Top right. This is phase 1 of 3, okay? And I say that because here's the mechanical room. So instead of having cooling towers, boilers, fluid coolers, whatever else on these buildings, this is your mechanical room, okay? So these buildings are basically pulling off an ATL, and we're providing, I'll get into it, we're providing, I believe it's 66 minimum and 77 or 78 degree maximum year-round ATL water, ambient temperature loop water. Every one of these buildings has water source heat pumps in there or water-cooled refrigeration for their supermarket, convenience stores, and things like that. They're also doing some snow melt on there as well. The tanks, you look in the background, you think, my gosh, those tanks are pretty big. Those tanks were sized for full capacity estimated for phase 3, phase 1, 2, and 3. So all they got to do is they've just got to add an additional SHARC units every phase, okay? So what that looks like, the way it was financed, what the cost, I know you guys wanted to see some numbers, but this is an overall aerial view of the campus. You can see it's kind of sprawled out. The total cost was $8 million. The total operating cost was $8,100 a month, and that's for the SHARC plant, the ATL, and the district system. That's all the pumps, it's all the drives, it's everything that's included in that. So each tenant or building owner, it doesn't matter whether you have an apartment, a condo, or you own the supermarket, you're sent a bill every month for $20. Okay, sounds crazy, doesn't it? So you get a bill every month. It's a passive ambient energy bill is what they call it, 20 bucks. The actual operating cost that the developers and the operators see is $4 per tenant per month. There's 1,850 tenants in here. So $4 is what it's costing them. They take the $16, which is the residual, and they accrue it to pay for any advancements in that system, that phase one, and also to set aside to fund phase two and phase three, okay? So you're really looking at, I don't like talking about, I've been doing GEO for 4+ decades, and I don't like talking about simple paybacks. It's usually life cycle cost, return on investment. But if you do look at a simple payback, with this simple structure, it's 100 months, less than 100 months. So that's pretty effective. The other thing with the ATL being able to provide 66 to, I believe, 78 degree water to all of these buildings, it maximizes the capacity and it maximizes the energy efficiency, the EERs and COPs of every single one of these hydronic units that's operating in these buildings. So I see it on the bottom, 66 to 80. So I was sandbagging there for a little bit. So the last one is a project in Denver, Colorado. It's a National Western Center. This is an ESCO, okay? And so the ESCO partner, it's just a flat ESCO with the city, and it's about 230 acres, and there's an old historic. You can see the photo of the campus up on the top right, and it's old historic showground, sail barn, you know, things like that. But now what they've done is they've got a community college on there. They have supermarkets. They have multifamily apartments, condos on there. They also have restaurants and multi-use office buildings, all right? So what we did on this job is we basically tapped a 72-inch sewer line. And you can hot tap, meaning an active. You can hot tap a 72-inch sewer line. Now, I wouldn't suggest you stand real close to it and you let the people that really know what they're doing do it. But we hot tapped a 72-inch sewer line with a 16-inch pipe. We ran that 16-inch pipe to this wastewater holding tank. So this wastewater holding tank was sized as a thermal energy battery or thermal storage, that if the fluid would ever fluctuate from that 72-inch to the 16, then our wastewater holding tank, very, very similar to the way we size the wastewater holding tank with our Piranha unit in a single building, you're going to have ebbs and flows of effluent discharge. So you basically just size that tank. And you try to do it correct. There's no reason to way oversize it. I mean, kind of being one, a lot of engineers have a tendency to say you want to measure with micrometer, mark it with chalk, cut it with a torch, just put in bigger and better and cover your butt, you know, that kind of thing. But you really don't need to do that. So we've got the science and the capability to be able to properly right size that storage tank. So all the fluid comes into a storage tank. We pump out of that storage tank into two, you see on the bottom left, two SHARC 880s. Those SHARC 880s then are recovering and transferring 3.8 megawatts of thermal energy to this ambient temperature loop that you see on the screen. The cool thing about that is you have some buildings that are dominantly heating. You have some buildings that are dominantly cooling, like your supermarket. You've got some buildings that they've got a little bit of diversity there within their own building, so they're heating and cooling. But then the net is that as buildings are drawing energy off the ambient temperature loop and other buildings are putting energy back into the ambient temperature loop, then it pretty much equals that out. So we're providing 55-degree minimum ATL temp and 78-degree max ambient temp loop temp to all of these buildings throughout this whole campus. Okay? So I guess one of the last comments is the picture on the bottom left. Whenever people start talking about sewage, they kind of gravitate towards an aroma okay? So these systems pass that sniff test. And the best way to validate that or describe that is this picture in the bottom left-hand corner. This is a mechanical building that was built because they're going to add on to the National Western Center. So right now we've got 2 SHARC 880s in there. You can see absolutely beautiful mechanical room. So we have civic groups in Denver. You've got ASPE, American Society of Professional Engineers. You've got ASHRAE folks. You've got, you know, the Butterfly Academy or whatever the heck you want to call it. They're all showing up. They're having meetings in there. They're having lunch and learns. They're enjoying their lunch. They're enjoying their banquet. And 8 to 10 to 12 feet away from them, we are moving 3,000 gallons of raw sewage. Okay? That's passing the sniff test. All right? That's all I got for you. Thanks for the time.
That's awesome. Thank you. That was awesome. Who wants a baby shark? I want a baby shark. Amazing. I can see why John wanted you to explain the technology a bit before getting to the case studies. I think that was really helpful. Thank you so much for that. So we have some time for questions. I have a couple questions, but I'm way more interested in your questions. So while Ron asks his question, everybody else, please be thinking of questions you want to ask. We've heard some really great stuff here about what the challenges are, right, to energy as a service model, what the opportunities, what optimal needs are to make it work, and then we've got a really wild technology that I just think has a ton of promise, and it's really exciting, you know, to think about the future of this. Okay, Ron, hopefully we've bought everyone some time. You're thinking of your questions, yes? Yes? All right, Ron in the back, and then I see. Oops, Gene has
Thanks,
a question.
Venetia. Ron Kamen, Earthkind Energy Consulting. So I come from a long clean energy history, and when I think of thermal energy as a storage, thermal energy as a service, I think of power purchase agreements like we do with solar. I think of energy efficiency performance contracts like we do with a bunch of efficiency stuff. Cameron, I think you did a really great job of this following up on the IRA constraints on doing thermal energy as a service. I guess my question to you, Cameron, is, are there ways of doing this that overcome some of the existing challenges? My question to Tim and to Michael is, how does this impact your business models? Because I didn't really hear thermal energy as a service from you guys. And then Michael, in particular, I'm just wondering about the maintenance on the SHARC systems overall. So those are my questions, if you would indulge me.
Yeah, on the question around overcoming some of the challenges, I think the best structure that we have available to us to overcome the energy as a service challenge is probably an installment sale. It was referenced in one of the panels earlier. The limitation of an installment sale, though, is it will not be treated as off balance sheet, right? So you can't get that same benefit that you do for like a solar PPA, for example. The other challenge with an installment sale is there's often cheaper sources of capital out there, right? So it may not be in the end user's best interest to pursue that installment sale with a geothermal developer. They may be able to access lower cost of capital through their own channels. So those are kind of the challenges that I think are, you know, an installment sale brings along with it.
Yeah, so I think when it comes to developing an offering and rolling out an energy as a service for geothermal, the customers that I've dealt with, predominantly real estate developers, tend to be quite risk averse. And so going back 5 or even 10 years, often what I would hear is, well, show me where you've done this before. Show me a building that looks like mine that has an energy as a service operating for geothermal. And that was a hard thing to point to. There wasn't many examples, if any. And this morning, we heard, I think at the 9 o'clock opener, you know, some new construction, new buildings, you know, pretty premier residential towers, right, in New York City that are being built with geothermal. And so while they're maybe not energy as a service, we can at least now point to some examples and say, well, real estate developers in New York City are adopting geothermal for residential buildings. It works, right? And so I think that's a big step in terms of being able to de-risk and talk about energy as a service and point to examples that we haven't had in 5 and 10 years prior. So I think it's maybe a transitional, slow sort of movement towards that. But I think being able to point to projects is huge when it comes to selling energy as a service for future projects as well.
Yeah, I'm not real sure as far as the project SHARC's involved in. I mentioned public-private with Alexandria project there in Seattle, but then obviously the ESCO that I used a couple examples on. And then there's a model, it's EUSC, it's Energy Utility Service Contracting. So that's in play. The other thing that's in play that I would have loved to show this slide or this project to you, and Cameron kind of mentioned it, but in just outside of Vancouver, there's a community section that is called Falls Creek, and it was actually developed for the 2010 Olympics. Or maybe it's Timothy that mentioned that. And sorry to give you any credit, Cameron. and so the community, the residents and the citizens actually got together and formed a utility, and we're capturing this thermal energy, and we're preconditioning for a district heating system of 23 million plus square feet. Okay, so there's so many different models, and then you look at energy as a service, and you start looking at public, you look at private, you look at ESCOs, you look at EUSCs, and then the other one, the most simple model is just, you've got a magic box and a magic system that does great things, and just lease it to the owner. Get a portion of the savings over a period of a year.
Okay, I think we had another. Oh, you got one there? Okay, and then one up there front.
Hello, this question's for Michael. Obviously, New York City already has a lot of sewer pipe installed, and one of the biggest challenges for new district energy systems is installing new pipe, especially somewhere like New York City. So I was just wondering if you have any thoughts on installing your SHARC heat exchangers on existing sewer lines in areas where it's quite congested underground, and what challenges that you see to that, and what opportunities you might see for that in somewhere like New York City. And my name is David Lowen, National Grid.
Okay, great. Thanks for the question. I'm not quite sure I'm going to answer it yet, but I'm going to take a shot at it. As far as connecting a sewer line for wastewater energy transfer to, say, a SHARC system, if you're connecting to the municipal sewage lines, it's not different than if you're building a new building and you're connecting your sewage lines or discharge line from that building to the sewage system, okay? So it's just we're changing the direction. We're trying to pull the sewage. If you are pulling it out of the sewage lines, you're trying to pull it back into a holding tank, and then use that process as I described with either the SHARC unit or the Piranha. There's also an option if it's a multifamily building, or if it is a building that has ample amount of volume of effluent, then you don't have to worry about pulling from the current sewer line or sewer distribution system. Is you capture that effluent into the holding tank, you harvest that thermal energy, and then you use the line you were going to use anyway from the holding tank back to the sewage line. That could be retrofit, and it'll also be new construction. You're going to have to make that hookup anyway. You're going to have to tap that anyway. So did that answer the whole question, or was another part of it?
I think, yeah, over here.
Hi, I'm Jean Bergman from Sane Energy Project. It seems to me, and it's been so clear these last 2 days, that our technology for energy systems has outpaced our systems for regulating it, for setting policy, for rate setting. And you mentioned, actually, was it this morning or yesterday morning, about whale oil, right?
Yeah, yeah.
So we're at another inflection point, as they say, with these new technologies no longer being the giant investor-owned utilities. There are a few, but these alternatives that shift the ownership paradigm and create all of these other countervailing opportunities. And I wonder if any of you, including you, Venetia, can suggest a sort of a different vision, like not one that was set by FDR almost 100 years ago, but what would the regulatory system that embraces and expands these highly efficient and fossil-free alternatives look like? And how can we move in that direction?
Yeah, I'll jump in just because I feel like you're asking a policy question in a way. I mean, I know it's deeper than that. You're asking on the regulatory front, and there's financing. Your basic point is the technology has outpaced all the ways that we kind of conceive and structure energy today. Right. Yeah.
Which is an older model.
Right. Yeah, I guess I spent most of my life in the public sector, so maybe my mind just tends to go there. But I think especially what SHARC is opening up is you kind of think of in New York City anyway, you've got kind of Con Edison's infrastructure in the streets, and you've got DEP infrastructure running right next to it, essentially. And I think that it's sort of conceiving of marrying those two systems in a way. Like you could, I mean, I also think about the pace of climate change, and I was talking to someone in this room who shall remain nameless, who is, panicking because he has grandchildren and is literally panicking thinking about climate change and thinking about the pace of doing this, that you can do it sort of block by block and piece by piece, but I'm having these sort of Robert Moses visions of like, we've just got to take the chocolate and the peanut butter and kind of, maybe that's not a good analogy here, but you got to kind of put the two systems together at large. What's really radical about this is there's no geo component here, right? There's no loop in what you're talking about.
Yeah, I mean, there can be.
There can be, but there doesn't need to be.
And so I've been a geo junkie for 4+ decades, and I can't set that aside. So if the SHARC technology and ground heat exchanger geothermal technology is a perfect blend, and you put the two together, and you've got, you got a great product. But we don't rely on the Leland project I introduced in the end. We asked them because it made sense. They're putting a ground heat exchanger field in phase 2 at Leland because of the nature of the system and the usage and the lower effluent and things like that. So there are cases our technology needs geo, and there are cases that a geo field got out of whack, and how are you going to fix it? We can not only fix it and control that temperature creep and keep them in that sweet spot window, but we can take all that energy we pulled to keep it in that sweet spot window from the ground heat exchanger and use that for potable hot water heating or cooling or snow melt and de-ice. So that energy is still not wasted.
Yeah, so Jean, it's a really good question. Like thinking of that, like if you go behind the curtain at Con Edison and you look at the electric network maps for Manhattan, I mean, it's just amazing. But it's sort of, I still, and maybe I'm biased as a utility, think that you need some Uber entity that could be balancing across large geographies if you're going to do this at scale. But maybe, but these are also interesting other models, right, that we're hearing about that maybe you need to experiment in a couple different kinds of ways, it sounds like. I know we're at time. I want to be very respectful to the conference warriors, as Cameron said, you've made it to the end. It's 4 o'clock, so we're going to wrap, but everyone is definitely here. Really, let's have a round of applause for our panel. Super strong ending here. Really want to thank you guys. That was fantastic. Enjoy. Yeah.